Um, this is an example of seeking a good contrast when we have some disturbance. So here I pick the disturbance to be underneath the grating, and then I move it a bit. You can see this. You can see this here. This will be the direction, and if I omit the mid layers, you can see the upper grading and the lower grading as shown here. So the unit cell will be around the outer grading, and if we see the if we present the near field will look like something like this. So I check it for several theta, but here it's this certain NA. Just to remind the monitoring notation, so above the grading will be RG or just G, and at the space will be noted as S. The left graph is a spectral information of total energy or density of energy at the near field. So to get a good contrast at the far field, we first need at least to have a good contrast at the near field. So if this is the total energy of S and G, the blue one, and we extract the ratio, so you see here the ratio S over G, where 1 is found here and here and here, it means they have the same energy, like here, 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 and so on. We would like to have a good contrast at the green, and maybe to choose a smart filter that gives good contrast in several areas, like here, 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 and here. And if we accumulate these narrow bands around this spectral range, we can accumulate good contrast or good demanded contrast for S over G or S minus G over S plus G. So these were the results for EX illumination when the polarization of the light is 0 or set to 0. And here we have without the disturbance, here with the disturbance at the area of the S and at the area of the G. And we'll expect that at least the contrast without the disturbance won't change. So this picture is better than this one, for example. And this at Y direction when the polarization set to 90 degrees. So this is the without disturbance, and this is with disturbance. Again, we will look for the best result to have no change at the polarization. And this is unpolarized, is when I'm transmitted X and Y at the same time. It equals it equals to the simulation when I'm transmitting the light at 45 degrees. So, and this is the summary of all of them. So the example for polarization and wavelength realms to choose for maximizing contrast between G and S area couldn't get good result for unpolarized at any wavelength. So we will choose in areas. For example, here I choose 602 nanometers at the full width half maximum of 50 nanometer, and you can see here that the contrast is kept pretty well. Of course, sometimes you'll find better solutions, but here the EX is much more sensitive, or can produce good results for good contrast between S and G. So this summarizes it. In this particular upper grating, the EX field, see the grating fine pitch better than EY illumination. I ran the simulation for only 3 layers to see their reaction to polarization. It is not exactly cheating if we want to see general behavior of the field. Hence, we indeed cannot deduce about the quantity of the energy compared with the whole stack.